today we will talk about a generic security mechanism that is called secure socket layer and transport layer security. Let's see what is the agenda. So this is what I intend to discuss in today's lecture. We'll see the what is secure socket layer, how it actually works, and what are the protocols involved, and then we'll see transport layer security. Fundamentally, SSL, secure socket layer, and TLS are more or less similar. So we'll understand what are the differences with respect to SSL, the differences that are there in the TLS, and then at the end I am going to talk about one popular application, that is the HTTP. So that is the agenda or the goal for today's lecture. So let's begin with generic discussion. We all use web for many things. We do online transactions, banking transactions, we give credit card information, and whenever we do this transaction or with your bank accounts, so you can see that the communication is basically, you see a padlock at the top and it is written as HTTPS. So here HTTPS means HTTP is an application layer protocol. That S stands for security. Basically, it's operating over the SSL communication. So that is the roughly the idea. So what we want to do is how exactly this security is given to the HTTP inside when it communicates. So that is what the goal. So just to recap your memory and give some context to the discussion, what we saw in the previous lecture is, so if you look at, we saw the email is one application. Whenever a mail is sent, so this is, you can think of this as application layer, and then below that you have the transport layer, and below that you have the network layer, and below that you have the link layer, and then the physical layer. And on the other side also you got the similar structure, the physical layer, the link layer, the network layer, and the transport layer, and finally the application, which in this case is the email application. So when we send the data from, particularly when I send an email from my system, so when it is supposed to go to the other end, when somebody who is the intended recipient receives that, so that is also an application. So when we discuss SMIME operates at this layer. So whenever something is encrypted, it is encrypted at the application layer. So email content is encrypted, and the SMIME itself is operating or working. The implementation of the SMIME itself is at the application layer. So this is the compared to that, the difference between the email communication and the TLS or the SSL is, unlike the previous SMIME, this operates at the more or less at the transport layer. Here we are talking about the, it is not exactly at the transport layer. You can think of in between the application layer and the transport layer. So the advantage that goes with the SSL or TSL by operating at the transport layer or in between the application the transport layer is, you can use the TLS or the SSL for many applications that you cannot do with the SMIME. SMIME is only meant for encrypting or providing the security to email communication and nothing more than that. You cannot use it for HTTP or other similar applications. So that is one difference. So with that background in mind, let's see what is the SSL overview is. So it is meant for providing reliable end-to-end communication. Two parties are engaging in some conversation, and what SSL says is, for the applications, you give me the data, I take that data, and then I transfer it to the other end by providing the security, which is the encryption. And the application at the other end can actually pick up the data from that tunnel and then process the data. So that way the security is end to end. And then in addition to encrypting the data that is transferred between the two ends, it also authenticates the peers who are engaging in the communication. If you go back to the slides, what it says is, if the this is client 1 and this is client 2, or you can call it maybe as a server, doesn't matter. So the client is authenticated to the server and the server is authenticated to the client, both ways. Although practically at the implementation level, when you deploy it, particularly if you take the case of the HTTP, typically what happens is only the server identifies itself. So when I do the transaction with in my bank account, my client, or I want to make sure that I'm indeed exchanging the communication or establish the communication with the banking server, nothing else. The server identifies itself, meaning the server is authenticated, and in most of the cases the client is not authenticated to the server. It doesn't matter who the client is, who is actually engaging, from where I log in. So whether it is the system number 1, 2 or 3, as long as I provide the right credentials to the application layer, when I give my username and password at the my bank account, it's actually the authentication is at the application layer. When I am talking the authentication now with respect to SSL, it is the transport layer authentication. So although you can use authentication mechanism in both directions, but most of the times in practical use cases, it is only the server which actually authenticates itself. And as we discussed, it provides the confidentiality of the data transferred. How do it does? By encrypting the data that is transferred. So, but one difference is, encrypting the data means that when I am operating at the application layer, I take pieces of the application, whatever chunks that is given, and then I encrypt those messages. But here, what the TLS or the SSL says is, you give me any byte stream, as long as it is, I receive something from the application, I am just encrypting that. So it is not encrypting the message per se, every message. So message 1, message 2, message 3, there is no difference like that. I just take the raw data as it is and then encrypt that data and transfer it to the other end. That is the meaning of the establish the secure tunnel. And as I said, it is application agnostic. It is meant to be used with respect to different applications. So if you use the SSL or the TLS, what it provides is, it prevents eavesdropping. Somebody who is sitting in the middle of the conversation cannot actually make out what is going on because everything is encrypted. It also provides security against the tampering. So somebody who is sitting in the middle cannot actually manipulate the data that is transferred between two systems. And somebody cannot fabricate a message. He cannot worry on claiming to be other party sending the data is actually one new message cannot be fabricated and sent to the other party. So it provides all of this. That is essentially what we discussed in the first lecture. We required that confidentiality, integrity and the authenticity of the data. So in nutshell, SSL or TLS provides all of them. So although we didn't talk about integrity as of now, but it is also there. And its biggest advantage is it works on top of the TCP, and as a model you can install. It does not require any changes to the operating system kernel. Typically the TCP/IP stack that we use is implemented as part of the kernel in the operating system. So if you have to change that, then it's actually a little tedious. But a good news is, SSL doesn't require any of those changes. So it can directly go and sit on top of the TCP/IP stack that you got and then start functioning. So SSL is not a single protocol which actually does all of this. Actually, 4 protocols. One is the major chunk which actually does the work is the something called SSL record protocol. This is the one which actually encrypts the data and also provides the integrity of the data whenever I use this protocol and transmit it. And that you can call it as layer 1 or 2, generally called as layer 2. So this is layer 1 layer of the SSL protocol, and that sits on top of the TCP. So application is here, TCP is here. In between these two, this protocol actually functions in between the TCP and the HTTP or any other application. And on top of this, above layer or layer 1, it has got 3 sub-layer protocols. So one is called SSL Handshake protocol, the second one is called SSL Cipher change protocol, and the third one SSL alert protocol. These are kind of, you can think of them as the control plane protocols. They are meant to establish the connection between the two end systems and then kind of monitor what's going on between these two, whether things are okay or something need to be changed, or is the other party need to be alerted, or stuff like that. So in nutshell, this is what the management operation or the control plane operations are done by these 3 protocols, which are at the layer number 1. And the actual data transfer, the encryption, whatever the application is giving, that is carried over the SSL record protocol. So let's take a look at what are the details of these protocols, in fact each one of them, and then see what exactly happens there. So to begin with, let's start the discussion on the SSL record protocol. So this is actually the heart of the SSL. Whatever the encryption or the whatever data that is transferred, it is actually transferred through this. So what it does is, it receives the raw bytes from the application. So the original data that written is, this is the application data. So that application data, this might be the data given by HTTP. Take that data and then divide that data into fragments, so small chunks. So raw bytes, you take it and then you divide them, bunch them into fragments. So the SSL puts a limit on the quantum of the data that can go inside one fragment. That turns out to be at the max 2 to the power of 14 bytes. So in one chunk or in one fragment, you can have these many number of the bytes. This is the maximum limit. So you cannot carry beyond that. So it can be, actual data can be smaller than this, but there is something that is done. So we will come to that in a minute. So at the max 2 to the power of 16 bytes, and the data can be in fact less than that. So once you fragment that data, the next step that happens is you use a compression algorithm and then try to compress that data. So this is actually a lossless compression, meaning data is not lost. There are, whenever you talk about the compression algorithms, there are 2 types. One is the lossless, second one is the lossy compression. Lossy compressions are not used in typically HTTP communications, but sometime in other domains. Maybe if you want to compress an image or a video, so that time you can afford to lose some information in the image. You can make the image slightly blur and use it. That's okay, but not here in this context. When you use the for banking transaction, we don't want if you transfer $1 million, the leading one is actually disappeared during the compression. That should not happen. So it actually doesn't allow that to happen. So compression always does not necessarily need to reduce the size of the data, but sometimes it can also because it's not lossy. So it might, if you transform the input data using an algorithm, it might slightly increase as well. So then SSL actually puts a limit on how much that increase can be. The compression reduction can be up to any level, but the increase can be limited to certain bytes. So once you apply the compression, you take that compressed data, and then at the end of this, you append something called as the message authentication code, or called as the MAC. So MAC is simply the you take the hash of the algorithm along with the key, and then you attach that. So basically, this is a hash algorithm, but it has got a key. So we did discuss this, how the MAC is generated. In the next slide, I have got the details of how exactly this MAC is calculated. For the time being, assume that is there on but it is calculated on the compressed data. Once the MAC is attached on that, you take this whole bunch, the compressed data and the MAC itself, as input and pass it on to an encryption algorithm. So that will bring the security to the data that is emitted. So the data becomes random. So once you encrypt that data, then after this encryption, you attach a header known as the SSL header. So you take the compressed data plus the MAC, encrypt it, and then on top of that you attach this SSL header and then transmit it to the other end. So let's take a look at how the entire bunch look like. So this is the encrypted data, is what the compressed data that I was referring to, and this is what the MAC is. So MAC is one component, the encrypted data is another component. On top of this, you attach this. This is the SSL header. It has got these many, the header has got these many 4 components. Basically, it identifies what is the application data the SSL protocol is carrying. That is the content type, the first element within the header. And then it might be HTTP or other applications. So if you use, for example, FTP, so it tells that this data is actually belongs to an FTP application or HTTP application, something like that. And then the second component is something called as the major version. So this major version is the SSL start at the version number 3. In most of the cases, it is, if it is in SSL, then it's a version number 3. And then there is a minor version. Sometimes historically, when it was early stage of the development, people used version number 1, 1.1, something like that. So the most that is where the SSL stop is version number 3, and the minor version is usually set to 0. And then subsequently, this is the third component. Then the fourth component is something called a compressed length. So length of the data. After the compression, whatever is here, once the compression has happened, so what is the length? If let's say here 100 bytes, I'm saying the 100 bytes. So sometimes to make it work with other algorithms for calculation of the MAC or the encryption, they do require, particularly if you use the block ciphers for calculating, encrypting and calculating the hash values, then they do want the data to be of certain length. At that point of time, what can happen is, if the data is not exactly ending at the block that the algorithm wants, so at the end you may put some kind of the padding. So the data all the way from here to here, adding, this is the last portion, as you can call it as the padding. So this padding is a data that gets added to it to just make it multiple of whatever the block cipher requires. So you use this padding, and this hash is actually calculated, but the MAC is actually calculated using this padded version of the data. So it takes these many components. One is something called as the secret key, and the second one is the data and plus the padding that I was talking, and then the sequence number. In SSL protocol, every piece of the data is actually identified by sequence number. This is a different sequence number than the TCP uses. TCP also uses a sequence number, but that has nothing to do with the SSL sequence number. So this is the application data that the sequence number of the SSL protocol itself, not of the TCP. So that is how the MAC is calculated, and that MAC is the one which goes here and then gets encrypted. So that is what happens in the SL protocol. So that SL particular record protocol. So very simple operation. All that you do is take the data, divide that, compress it, and then calculate the MAC, including the padding and the sequence number, and attach the MAC to the end of the compressed data. End of the compressed data means plus the padding plus the data, and then you encrypt it. After doing the encryption, you attach a header, so it has got these many details, and then you send it. So that is the simple operation of the SSL protocol. So this happens in both the directions. So whenever client wants to send something to the server, if you take the HTTP as an example, or the server wants to send something back to the client, in both directions, so this message structure is used. So that is about the SSL record protocol, the actual data transmission. But now let's take a look at the management protocols that I was referring to. So the first management protocol begin with the something called as the alert protocol. So alert protocol is meant to communicate the errors and the warnings that are generated during the communication. So those errors might be at the client side or the server side. It might be just a warning which you can live with, or it can be a message which is something called as the fatal. So if it is a fatal error, then the two parties need to end the communication immediately. So either it's a warning or it's a fatal. If it is a fatal kind of the error, then it's actually the connection is terminated. And the important thing is, these alert protocol messages, they are of the 2 bytes. The first byte indicates what kind of the error or the message it is, and the second byte has got a code. So that code is actually taken and then interpreted. What you need to do with respect to the existing connection. And these messages, in fact, are also encrypted and asked as per the ongoing communication. So you establish a SSL connection between two endpoints using some kind of the encryption algorithm and some algorithm for the MAC calculation or hash generation. So using the same mechanism, you also use some compression algorithm. Whatever you encryption algorithm or compression algorithm that you use for encrypting the data given by the application, the same set of algorithms can also be used to encrypt and compress the SSL protocol messages as well. So the same 2 bytes are taken and then compression. I don't know how much compression it's actually used at the end, but you can in fact use that encryption compression with them. So there are a bunch of error types and the error codes. So these are the common fatal errors that you can see. So unexpected message which is not supposed to be received, bad record MAC, the MAC actually calculation fails at the other end, then the other party can tell that I cannot actually understand this MAC, can you send it? Or if the compression algorithm fails, then also it can indicate that the decompression could not be done. Or the handshake is used for establishing the connection right at the beginning. If there is an issue with the establishing the connection itself, that time also you can use. And if there are some illegal parameters that are passed to the SSL communication channel, then that can also be identified. This we'll see what kind of parameters are transferred during the connection establishment and other phases in a minute. So that is what the SSL alert protocol is all about. Very simple protocol, only 2 bytes. One is indicating the warning says, and the second one is the code. And even simpler management protocol in the SSL suite is basically 1 byte data that gets transferred, called as the SSL change Cipher protocol. This protocol is used when you want to terminate an existing connection. Whenever the tunnel is established with a two-end system, you want to terminate that time you can send this message. Or during the ongoing conversation, if you want to change some of the algorithms that are used, for example, the encryption algorithm need to be changed, the compression algorithm need to be changed. Oh, it is as good as I no longer want to use this set of the protocols, but I want to switch to something else. So that kind of the key I want to renew or change that time also you can use that. Particularly any changes in the ongoing communication if you want to make, including the termination, that time you use this protocol. And interestingly, again, although this is a 1 byte protocol, the same encryption and the compression methods that are used for data is also applicable for this communication as well when the data is sent using it. So the third management layer protocol, which is the most complex one out of the 3, is something called SSL Handshake protocol. Before we actually go into details, let's look at its structure. So this SSL Handshake protocol has got 3 components. The first component is the type message, that is the 1 byte, and then second component indicates the length of the message, whatever is carried here. So that length is indicated is in here, and the actual content was here. So why this type is basically to identify whether what the client is sending to the server and the server is sending back to the client. So I just give an example. So at the time of the initial communication, the client and server might exchange certificate. So it might tell this is the type of the message. They might also exchange some random number selected to generate the session keys. So it actually identifies what kind of the message it is. So in the next slide, the details are there, what all kinds of the messages are there. So all of them use this generic structure, these 3 components. The first 2 are fixed, 1 byte and 3 bytes. The content itself can be of either 0 or more length. So SSL Handshake protocol is a management protocol. It is, as I said, it's quite complex. It operates in 4 phases. So phase 1, phase 2, 3 and 4. And these 4 phases, in the first phase, basically client and server with respect to the HTTP, if you talk about, they say that hello to each other. So we do want to, I am so and so, I want to talk to you. And the server says, I am so and so, okay, I am also willing to talk to you. And in the second phase, the server might send its own certificate to the client, basically to authenticate, to establish that the client is indeed communicating or establishing connection with a genuine server. So the server sends a bunch of details back to the client. And the third phase, sometimes the client might also send a certificate to the server, but that is an optional thing. And in the process, they might also derive something called session key. So that session key is used for encrypting the data. The certificate has got the public key information of the peer, but that key is not used for data encryption. Data encryption happens using a symmetric key algorithm, and to that you give a session key as an input. So in the third phase, that is actually calculated and derived. And in the final phase, you negotiate, okay, this is the key that we're going to use, and this is the method algorithm we are going to use for encryption, for example, DES. and then this is how we exchange the key, all the parameters. This is the compression algorithm that we use. All those crypto parameters are and the algorithms are negotiated, and then it's done. In the fourth page they hang up. So we are all set to go now, and now we can communicate with each other. So that is roughly what happens. So let's go and look at the details of what exactly happens in each one of these 4 pages. Let's begin with the phase 1. In the phase 1 is initiated by the client, and a message is sent to the server, and that message has got these 5 quantities. The first message, it identifies the version number of the SSL protocol that the client can support. This is the highest version, meaning if the client can understand only version 1 and 2, it will tell I can understand version number 2. So assuming the backward compatibility is there, the server can either choose to talk with the client with version number 1 or 2, either of that. So in any case, the client, whenever it sends a message, it identifies the highest version that it can support, maybe 3.0, 2.9, something like that. And the second quantity is something called as the random number. So this random number has got 2 components. One is the 32-bit timestamp plus another 28 bytes of the pseudo random number. This is generated with the random number. You take the timestamp value from the system clock plus the 28 bytes you take from the random number generated. These two are sent as one entity to the peer. Basically in this case the server. So why this is required? This is required basically to derive some subsequently the session keys. And the session itself is identified by session ID. This is a variable number, variable length text, might be having the only number and alphabets as well, a combination of them. And the fourth parameter is because cyber suit. It is where the set up the cryptographic algorithms and the key exchange methods that the client can support. It export all of them to the server. So these are all the things that I am going to understand. I can use those many numbers of protocol. And the last thing is the compression algorithm. Which compression algorithm is it? So let's say you have got bunch of compression algorithms. I can understand compression algorithm number 1, 2, 3 or whatever, all of them. So one more thing, when it identifies the set of cryptographic protocols that it can understand, the client actually orders them in the order of their preference. So maybe the crypto algorithm 1 is the preference number 1, crypto algorithm 2 is the preference number 2, and so forth. Crypto algorithm number n, and this is the preference number n. So why this is numbered, prepared? So for when the server takes it, it understands that clients wants to use this highest number, assuming 1 is the highest priority element or the algorithm. So the client wants to talk with using this protocol, this algorithm. So maybe if I support that, then I can use that as well when we start engaging in the conversation. That is the meaning of that. So these 5 quantities are sent as part of the client hello message. So remember, client hello message is the first this message. And in the phase 1 itself, the server also sends back a reply, which is more or less the echo of what the client has sent to the server. So the same set of quantities are there. The version number is there, and the random number, session ID, Cipher, accept, and compression algorithm. Version number is now, in the previous case, it was the highest version that the client can support. Here when the server sends to the other end, this is the lowest version that the server can support and chosen. So if the client says I can talk with you using version number 2.9, but I can also support 0.9. If the server can also support anything below that, it actually is whatever is the lowest that it has got in hierarchy, it actually chooses that, and then it indicates that to the client. and then a random number which is similar to what is chosen by the client is also included here. And session ID is just echoed back. Whatever the client has sent you just pull out that session ID. Maybe session ID in the previous case is 10. So this number is also set to 10 and sent it back to the client. And then out of the cryptographic algorithms and the key exchange method the client has identified, a server chooses one, and then usually taking into consider the preference that the client has given, and then it identifies, okay, let's start using these protocols, these cryptographic algorithms, sorry. And then it also chooses a compression algorithm that also the server indicates in the message. So that is about the server hello. Oh, there is a typo. This is not client hello. This is the server hello. Okay, please make a note. Yes. Okay, that's the client and the server hello. So the cryptographic algorithms, whatever the method that crypto shoot that I was talking. So these are some of the algorithms for different purposes that are supported. For key exchange method means for session key exchange methods you can actually use RSA, DP-Hellman or ephemeral DP-Hellman, anonymous DP-Hellman. These are different versions that the SSL supports. So you can identify when the client sends and the server sends, they can negotiate on this one. And then the cryptographic algorithm, the Cipher algorithm can be RC4, RC2, DS. These are all the supported versions in SSL version number 3. Going forward, there are a few more additions that are done. And then the MAC algorithm, MD5, SA1, you can either use the stream and or the block ciphers. The difference between block and stream cipher is the following. If you use a block cipher, if let's say the crypto algorithm takes some input, that algorithm is taking the fixed size input, let's say 10 bytes. And then it has got a key and it turns this 10 bytes into some output, let's say whatever might be the length. Maybe for the sake of simplicity, let's assume this is also 10 bytes. So you give the 10 bytes data and 10 bytes of the encrypted data comes. So if let's say I have the 100 bytes of the total data given by the application, all that I do is take 10 bytes at a time, give it to the cryptographic algorithm and then generate 10 bytes. And second 10 bytes that other than what is used here as again given to the algorithm, again same encryption happens and then you get back the another output. So another 10 bytes. You concatenate all of these and then you get one encrypted output. That is the block cipher. Every 10 bytes from the input is taken and then pass it on to the encryption algorithm. Then whatever the encrypted data you get, you concatenate that and then use it for transmission. Block cipher. So there is no connection between the first 10 bytes and the second 10 bytes. Unlike that, stream ciphers are actually used where you got once you do the operation on the first 10 bytes, whatever is the output that is generated, that is also fed as input to the second subsequent operations. So that is so you got a chain. One is you take one thing, encrypt it, and then you carry that forward to the next page, and the next page, and next page, so forth. So that is called the stream cipher. And then you got the different hash sizes. The hash size at the minimum can be 0, but in most of the cases it is not 0. Either you use the MD5, if that is the case, 16 bytes of the hash is generated, or MAC is generated. If you use SA1, then 20 bytes of the hash is generated. And then you got an initial vector. Some of the cryptographic algorithms requires the initial vector, initialization vector. So that is also the size of that initialization vector and the what is the key material, how you derive the session key, exactly that, and what is the component that is transferred is also indicated here. So this is what basically in the Cipher suite we are identifying what kind of the cryptographic protocols are used and the key components required to generate the secure data at the other end. Okay, that is about the phase 1 where the client and the server just said hello to each other.